Hello, everyone. In our last movie, we began to look at motion which we could call uniformly angular accelerated. Right? Big long phrase, right? But it was a new kind of rotational motion, right? But one that still had a constant angular acceleration. And we came up with the four kinematic equations that would describe that motion, again, very much like the linear analogy of uniformly accelerated motion. Well, now what we need to do is to connect the rotational to the linear, right? Because parts of objects, which are rigid objects rotating about a fixed axis, which are rotating, right? Those parts are also moving linearly. They are covering a distance in a certain amount of time, right? And we have kind of compared already how we can look at linear position and angular position, or arc length, right, and angular position, linear speed and angular velocity, right? And now we have to talk about angular acceleration and linear acceleration. Now, acceleration is always a little bit more difficult, and it's even more difficult in rotation because there's actually two kinds of angular acceleration. Okay, because two kinds of linear acceleration when there's a rigid object rotating about a fixed axis. And that's because it could be doing two different things if it's rotating. A point on an object that is in rotation, and a rigid object rotating about a fixed axis, is changing direction as it rotates. Right? As we've discussed before when we did uniform circular motion, objects moving in circles at constant speeds. But it also could be speeding up or slowing down as it rotates. And so these two different things have different components to their linear accelerations. Okay? And these components are perpendicular to one another. And we almost always speak of the linear acceleration of a rigid object rotating about a fixed axis in terms of these perpendicular components, not the overall linear acceleration, which we could certainly create if we had to, with a little Pythagorean theorem and an inverse tangent. As we know, right, if we go back to what we know about uniform circular motion, right, an object moving in a circle always has an inward directed acceleration, right, and an inward directed net force, which we called centripetal, right, when we looked at those. Well, a rigid object rotating about a fixed axis, a point on that object will have an inward directed acceleration, right, as it rotates, as it changes direction. We tend to call that now, rather than centripetal, we call that the radial component, right, of the linear acceleration, because it acts inward, which is along the radius. And we know what that value is, at least in linear terms, because we did a whole big lab on it and everything back in honors. We know that the radial component, or what we used to call the centripetal acceleration, is the speed squared divided by the radius. Right? And that would give you an acceleration in meters per second squared, and is completely due to the change in direction that it undergoes, that a point on a rigid object rotating about a fixed axis undergoes as it rotates. Lots of words in rotation, isn't there? And this is always inward directed or radially directed. Okay? But remember that we can convert linear speed to angular velocity using v equals omega r. So if we plug that in, we get this radial component of our linear acceleration is equal to the quantity omega r squared over r. Square it. Get omega squared r squared over r. Of course, one of those r's will cancel. And so we have two ways now to calculate that radial component in terms of the linear motion of that point on a rigid object rotating about a fixed axis, speed squared divided by the radius, or in terms of what it's doing rotationally, angular velocity squared times radius. This does need to be in radian measure, though. Remember, radians is a unit that's really more of a name than a unit, right? 1 radian is when your arc length and your radius are exactly the same length, right? So angular velocity would be in radians per second, which gets squared, which would be a radian squared per second squared, times the radius would be in meters. So radian squared per second squared times a meter is a meter per second squared. Right? The radians just disappear if you don't need them. Right? But you can't do that if this is in degrees or revolutions or something. It has to be in radians in order to be able to get out meters per second squared, right, for your linear acceleration. So again, this is the part of the linear acceleration that is due to changing direction. Now, this was the only part we needed in uniform circular motion in our unit on central force and honors, because we only looked at things that moved at constant speed as they moved in a circle, or things that we could approximate moving at a constant speed, right? Like the moon moving in a near circular orbit, right, around the Earth, or the Earth moving in a near circular orbit around the sun, right? An eraser on the end of a string that we whirled in a constant speed circle, right? Driving at constant speeds over circular hills or around circular curves, right? All those kinds of things. But it was always constant speeds. But what if you're speeding up or slowing down? Well, if you're speeding up or slowing down, if we think about, again, the linear analogy, that's going to take a torque. And torques are all about perpendiculars, right? This is the component due to changes in direction, sorry. So this is what we are going to call the tangential component of the linear acceleration. This is the part that only exists if there are changes in speed of the rotating object. So as this rigid object rotates about a fixed axis, if it is speeding up or slowing down, then it will have a tangential component, which will act tangent to the circle. Now, how are we going to calculate that? Well, let me go through a little proof here. Okay, the tangential acceleration is, of course, the change in the speed over the change in the time. That's just what acceleration is generally. But remember, linear speed is angular velocity times the radius. So if we plug that in there, we get that the tangential component of the linear acceleration of a point on a rigid object rotating about a fixed axis is the change in the quantity angular velocity times the radius over the angular time. Radius, of course, because a point on a rigid object rotating about a fixed axis moves in a circle. So the radius here is going to be constant, so we can pull it outside of the change in part. And then look what we have left. The change in the angular velocity over the change in time. You remember what we defined that as? We defined that as the angular acceleration, the rate of change of angular velocity. Plug that in, and we get an equation, a math model, sorry, to calculate the tangential component of the linear acceleration. It's the angular acceleration times the radius. Now, note again, this is due to the changes in speed of a rotating object. If the rotating object is rotating constantly, it doesn't have this because it has no angular acceleration. Right? So it has no tangential component. It still has a radial component because that point is constantly changing direction as long as it's rotating. The only way you have no radial and no tangential component to the linear acceleration of a point on a rigid object rotating about a fixed axis is if it's not moving at all. So this is the part due to the changes in speed. So, if this object that I used yesterday that's going to angularly accelerate, right, it would have a radial component acting inward, right, if we're looking at these 2 points out here, right, the brass masses that are at the ends. And we can calculate that radial component using either speed squared over radius or angular velocity squared times the radius. And it has a tangential component, notice, perpendicular to the radius by definition, that's what tangent is, of angular acceleration times the radius. And if you put that into motion, there you go. Notice that at any point, right, we can look at it and we can always draw the radial component and the tangential component. But do note that they are constantly changing direction, right, with the rotating object. Right? Those arrows don't stay pointing the same direction all the time. Right? They're constantly changing, but they're always radial or tangential. Now, technically, we could put these two things together. Maybe if we moved this down here so that it was head to tail, right? And then the total linear acceleration of this point would be you know, a line or an arrow going from here to here, right? Tail of the first to the head of the last. And we could do a little Pythagorean theorem and an inverse tangent. But again, they almost never ask for that. They might, you know, but usually they are focused on these two because they really have to do with different parts of the motion. The changes in direction and the changes in speed. Right? Give us the two parts. And notice the forces that cause them are in the same direction, right? The centripetal acceleration is due to a centripetal force, which is inward. It's along the radius. A change in speed takes a tangential component of a force in order to give a torque. If there is no tangential component to your force, say your force is completely radial, then there's no torque, and no torque means you won't have an angular acceleration, means you won't have a linear acceleration, tangential component. Now, what about rolling? In the past, we've looked to create relationships between what the center of mass is doing, right, and what a point on the outside or how the object is rolling, okay? And we're going to look at, again, perfect rolling, rolling without slipping. So there's no slipping at this interface, right? If there is, all bets are off. So let's watch this here, right? Consider a disk rolling without slipping. While most points, like a point on the outside, right, are going to move linearly and rotationally at the same time, the center of mass only moves linearly with a constant uniform acceleration we will call ACM for the acceleration of the center of mass. Okay, notice what's different here than in past units when we would look at like a box, we would think of the entire box as having one linear acceleration. Right? But now different points have different angular accelerations. I'm sorry, different linear components to their acceleration. Whew, a lot of words. As we proved earlier, though, if that's the arc length, we drop a little horizontal in here, that's the angular position it rotated through, the reference line rotated through, right? And if it's rolling without slipping, what's going to be true about the arc length? The distance a point on the outside moves through, and the distance the center of mass moves through? Yeah, those are going to be the same, right? So the arc length here and the distance the center of mass moves are the same. That is only true if it's rolling without slipping. Right? If it's slipping, the center of mass will move farther than a point on the outside. Right? When it slips, then it won't spin more. You with me? So the only time these two are going to be the same, right, is if it's rolling perfectly. So as we've done in the past, we know that the distance the center of mass moves is equal to theta r, right, the angular position it rotates through and the radius of the object, and the speed of the center of mass is equal to omega r, right? This is the angular velocity that it's spinning at and the radius of the object. Right? But remember, these are both center of mass, distance and speed. So, to get to the acceleration, let's take and divide both sides by time. With calculus, we could take a derivative with respect to time of both sides, but let's do this without all the fancy calc. Over here, I'm going to reorder this a bit, which I can do because it's multiplication, so it's commutative and associative. All right, so I'm going to write this as angular velocity over time times the radius. And then look at what we have. Over here we have linear velocity of the center of mass times the time. Well, what's velocity over time? It's linear acceleration. Right? This side is the acceleration of the center of mass. And over here we have omega over time, the angular velocity over time, which is going to be the angular acceleration. Right? So the linear acceleration of the center of mass of a perfectly rolling object is equal to the angular acceleration times the radius. This, by the way, this is not the tangential component to the linear acceleration of a point on a rigid object rotating about a fixed axis that we just derived earlier. This is the acceleration of the center of mass. All right, the acceleration of the center of mass. This is for rolling we're talking about here. Now, it's nice that it's the same, right? And these are the same conversions, but right, technically these are for center of mass, distance, speed, and acceleration. Perfectly rolling object, rolling without slipping. As in all cases, these need to be in radian measure, otherwise the units won't work. Right? Radians per second squared times a meter is a meter per second squared. Right? Won't work that way for degrees, revolutions, or so on. Okay? So this is how we can compare the distance, speed, and acceleration of the center of mass of a perfectly rolling object to the angular displacement, change in the velocity, and the acceleration, angular acceleration, angular velocity, of that object. If it's perfectly rolling without slipping. A lot of info there, folks. Got to practice now. Right? Oh, this is called the rolling condition, right?